Welcome to our overview of digital surveying in civil infrastructure. Discover how modern digital tools are advancing construction accuracy and transforming project outcomes. Let's begin with an introduction to digital surveying and its importance in today's civil engineering projects. Digital surveying uses advanced electronic devices and software or web-based platforms to collect and analyze spatial data efficiently. These digital methods enhance the accuracy of measurements and speed up data processing compared to traditional surveying. Cloud platforms also enable seamless collaboration and integration with design and construction workflows. Now, let's explore the core technologies that power digital surveying in civil infrastructure. Digital surveying relies on precision geolocation tools like GNSS RTK and robotic total stations for accurate automated measurements. 3D mapping technologies, including LiDAR systems and 3D laser scanning, create detailed models of terrain and infrastructure. UAVs or drones equipped with photogrammetry support rapid and cost-effective aerial data collection. Ground-penetrating radar detects underground features, and IoT sensors provide real-time structural health monitoring. Integrating survey data with digital platforms is essential for maximizing the value of digital surveying in civil projects. Building Information Modeling, or BIM, incorporates survey data into detailed 3D models for enhanced design and construction planning. Geographic information systems enable spatial analysis and mapping, while cloud-based collaboration allows real-time data sharing among stakeholders. Digital twins use survey data to create virtual replicas that simulate performance and predict maintenance needs. Let's look at how digital surveying is applied across various civil infrastructure projects. Digital surveying enables precise alignment and grading in road and highway construction. It supports structural analysis and monitoring for bridges and tunnels, enhances railway construction and maintenance through accurate track geometry, and aids in urban development and utility mapping for water, gas, and electrical networks. Next, we'll outline the standard workflow followed in digital surveying for civil infrastructure. The process begins with pre-survey planning, defining objectives, selecting equipment, and assessing site conditions. Data is then acquired using GNSS RTK, LiDAR, and drones. Specialized software processes and validates the raw data, ensuring accuracy. Finally, the data is transformed into models, visualized, and integrated with design and construction platforms for actionable insights. Digital surveying offers several significant advantages over traditional methods. Digital surveying reduces human error and improves accuracy with high-precision instruments. It speeds up data collection and automates processing, saving time and costs. Remote sensing technologies enhance safety by reducing personnel exposure to hazards. Instant data access and cloud collaboration also support real-time decision-making. Despite its benefits, digital surveying faces certain barriers to widespread adoption. Handling large volumes of data requires advanced storage and processing. There is a skills gap, with professionals needing training in new equipment and software. High equipment costs can limit adoption, especially for smaller firms. Ensuring regulatory compliance and addressing cybersecurity and data privacy are also critical challenges. Let's explore some emerging trends shaping the future of digital surveying in civil infrastructure. AI and machine learning are automating data analysis and identifying patterns in surveying processes. Autonomous systems, like self-navigating drones and robotic stations, are reducing human involvement. Augmented and virtual reality improve field visualization and communication, while integration with IoT and smart cities allows for continuous monitoring and predictive maintenance. Now, let's look at real-world examples demonstrating the benefits of digital surveying. In a highway expansion project, UAVs and LiDAR technology mapped terrain and monitored progress, reducing survey time and improving accuracy. For bridge rehabilitation, 3D laser scanning assessed structural integrity and informed repair planning. These cases show how digital surveying streamlines workflows, enhances safety, and supports data-driven decisions through skilled personnel and integration. To conclude, let's summarize key points and next steps for successful digital surveying adoption. Digital surveying delivers precise, efficient spatial data critical for modern civil infrastructure projects. Integrating with BIM, GIS, and cloud platforms enhances collaboration and informed decisions. Addressing data management and training challenges requires investment in equipment and personnel education. Adopting best practices will ensure precision, safety, and efficiency for resilient infrastructure development.